We're continuing to work our way through our handout on section 1.8. We're on page 6 where we get to properties of linear transformations. And so here we say let T be a linear transformation from Rn to Rm. So the u's and v's are vectors, the c's and d's are scalars or real numbers. And there are 3 properties listed here. Number 1 is kind of amazing. Any linear transformation will take the 0 vector in the domain and its image will be the 0 vector in the codomain. That always happens. We'll talk about that a little bit more in a minute. Number 2, if you apply a linear transformation to a scalar plus 1 vector times 1 vector plus a scalar times another, the image will always be equal to the scalar times the image of the first vector plus the scalar times the image of the second. And actually, number 3 is very similar to that. It's just saying if you have a finite sum, so if you have a sum that's a linear combination of p vectors, so you can think of the C1, C2 through Cp as weights, those scalars, the image of this linear combination of vectors will be equal to the first scalar times the image of the first vector plus the second scalar times the image of the second all the way down the line. So when you have a linear combination of vectors, if you just know the images of the original u1, u2 to up, basically you can figure out the image of any linear combination of those from that. And so let's talk about this property number 1 a little bit, because that's kind of profound. It's an unbreakable rule for a linear transformation that the image of 0 is 0. Now these are zeros in 2 different spaces though, right? This is an Rn component 0, this is Rm component 0, so the dimensions can be different. And to show that, we're going to go back to the definition of linear transformation, which was on page 3 up at the top. And what we're going to do is we're going to exploit that property about scalar multiples. So we're going to say 0 in the domain space can be thought of as the scalar 0 times any vector, where u is any vector in Rn. So when we apply t to 0, the 0 in Rn, we can write that as t of the 0 scalar times a vector u. And that, see, the 0 scalar we can factor out in front because that's a property of linear transformations. But now we're taking a 0 scalar times the image vector. And again, 0 scalar doesn't matter what that image vector is, t of u, because it's 0 times anything is 0. But now this is the 0 vector in the image space in Rm. So because we can factor out a scalar and we can use a scalar as 0 here, it makes this number 1 work. So that's kind of interesting, kind of amazing to have that property. I'll let you check 2 and 3 on your own. 2 and 3 are really just what happens when you combine the 2 defining properties of a linear transformation into a single situation. So let's go on to an exercise. Now we have an exercise here on the next page, page 7. And this is another case where we have this new language of linear transformation, but we're going to solve this problem by doing something we already know pretty well. So let A be this matrix. Consider the linear transformation from R3 to R2 defined by the image of x is AX. That means, so we're going to use matrix multiplication here to define this linear transformation. Find all x in R3 such that x is mapped to the 0 vector by this linear transformation. So I'm just going to translate this problem into saying we want to solve AX equals 0. When they say map to the 0 vector, they mean map to this. So after we take the product, we get 0. Notice that this is just a homogeneous equation. That we're going to solve. And if I set up my augmented matrix, it's going to be 1, 0, 0, negative 1, 2, 0. So there's the A matrix entries. And then I just write 0, 0. So notice that this is a 0 in R2, the codomain space. And I'm going to apply row operations. And again, the point isn't the row operations in these, it's just because they're not complicated to reduce these couple examples we've been working in this section. In fact, here, I already have, I'm almost in reduced form. I'm just going to multiply the second row by negative 1. So I'm going to just say row op, one row operation. And what we get is x1 plus 2x3 equals 0. We get x2 is equal to 0. So we got 3 input variables here. X1 and X2 correspond to pivots, but X3 does not, so X3 is free. And so let's describe our solution now in vector form with that X1, X2, X3. Again, so, well, X is in R3. The 0 is in R2, right? And so our X is going to be X1. If I solve for X1 here, I get minus 2X3. X2 has to be 0, and X3 is free. So I can express this X as, I want to factor out my X3 times negative 2, 0, 1. I'll rewrite this. So find all x here, we can say, well, it's going to be of the form x3 times negative 2, 0, 1, where x3 is any real number. So that's the general solution expressed in vector form. Or, if you want to be fancy about it, you can say we're looking at the span of a set containing just one vector. That means all scalar multiples of that vector, negative 2, 0, 1. And that describes all vectors x in this linear transformation that are mapped to the 0 vector. Okay, and so we're done with exercise 3. And yeah, there's one more portion to this section, and that will be in another video.